Hey guys, welcome to a new video. It's algorithm and data structure tutorial. In this video, we're going to talk about graphs, and first of all, we're going over the basic elements of graph, and we're going to talk about what a graph is and what we can represent a graph as in C++, and also like in other programming languages. And then we're going to talk about some of the more like practical examples of graphs and some of the algorithms that we can actually apply on graph, because graphs is probably one of the most used data structures when we're talking about implementing like real-time applications with algorithmic data structures, but also solving algorithm data structure problem. So it's a really nice and cool thing to know, and also like know when to use and know some of the algorithms that you can apply on graph to, for example, find the shortest path and a lot of other different kind of things. So first of all, let's go over the basic elements here of a graph. So first of all, we can see this kind of like a tree, as we already talked about in one of the previous videos. But in graphs here, we have a vertex here instead of a node. So it's kind of like the same, but instead of a node here, we have a vertex in our graph. And then we have edges here connecting all the vertexes, or some of the vertexes in our graph here. Like it can be connected in an arbitrary way, and then we'll have like different kind of graphs. So a graph can either be directed or undirected, which means that in this case here we have a directed graph because we have this arrow here. So if we're at vertex 1 here, we can only go to vertex 3, 4, and 2. And when we're at these vertices here, like we can't go back to vertex 1 again here because it is directed graph. But we could have an undirected graph where we could go from one node and back to the other node again. So in case we had an undirected graph, we could go from vertex 1 here to vertex 3 and then go back again from vertex 3 to 1 here. But we can't do it in this case here because we have a directed graph. When we're talking about graphs, we can also have them either weighted or unweighted graph, where in this case over here to the right we have an unweighted graph because there's not any cost on the edges, so we can move freely between these vertices here to other vertices, and it will only have a cost of 1. So it doesn't matter like if we travel to vertex 4 here or vertex 3 here from 1, it will have the same cost because we have an unweighted graph here, so the cost will just be 1 to travel to one of these nodes here. But we can also have a weighted graph where these edges here would have a cost. So let's say that it costs more to travel to vertex 3 than it does to travel to vertex 4. So this can be used in a lot of different kind of applications, and we're going to see some different kind of applications on, or like algorithms on how we can find the shortest path in a weighted and an unweighted graph. Let's say like for example over here we have different kind of like airports around in the world, and then we want to find like a shortest path between 2 or 3 airports in a weighted graph. Then we can have like the distance between the airports, which is the weight that is added to the edge between the 2 vertices or the 2 airports in that example. And then we can try to find like the optimal or like the shortest path between some airport to get to our final destination. So it can be used for a lot of different kind of things, and we're going to see this later on as well, and also have some code examples on how we can actually like find the shortest path in both an weighted and an unweighted graph. So we have different kind of operations in a graph. Like we can check if an element is in the graph, or we can do graph traversal where we're traversing around in the graph by the directed graph or undirected graph. And we can also add new elements to the graph and find a path from one vertex to another with different kind of algorithms. So here's just an overview over like the different kind of elements in a graph. So we talked about this undirected graph here and the directed graph, which just means that we can go like between the different kind of the vertices here when we have an undirected, and when we have a directed we can have like a direction set, so we can only go from one node and not back again. We can also have a cyclic graph here where we can see we have this cycle here around, so we go from one node to another node to the next node, and then we can go back again here, so we have like a cycle here in our graph. And we can also have an acyclic graph here where we don't like cycle around in the graph. So we have, for example, this vertex here, and then when we have left this vertex here, we can't go back again because none of the other vertices is connected or like has no direction back to the first vertex here that we started. And then we have the weighted and the unweighted graph here down here, where we can see that now we have added a cost to the edges in our graph. And we can also have a sparse graph here or a dense graph, where the sparse graph here is that we can connect the nodes here between each other, and we can also have the cycles. Where in this dense here, like we connect all of the nodes together. So if we're in this node here, we can go to all of the nodes here, and that means that we have a dense graph because all of the vertices are connected. So we have different kind of representations of graphs, like how we can represent it in code. So first of all, we have this adjacency matrix, which is really good for the dense graph that we just talked about. So this graph here that's connected to all of the vertices. So it's good for dense graphs, and it's a 2D array of vertices times vertices. So we can set it up as a matrix over here to the right, and we can see that we have an undirected graph here, and then we want to represent that undirected graph as an adjacency matrix over here. So we can see if we start here at vertex A here, we will just set up here. First of all, we initialize all of our adjacency matrix to zeros, and then when we add elements and directions and edges in our graph, then we will add ones over here to show like the kind of like the edge that we can go between some vertices. So in this case here, A, we can see that A is connected to B because we have a 1 here. So we can go from A to B, and from A we can also go to D here because we have a 1 here, but we can't go to A because we're already in A, and we can't go to C because then we have to visit B first, and we can't go to E because again we have to visit like D or BC first. So this is how we can set up an adjacency matrix for an undirected graph, and it's really good for like dense graphs when we have everything connected. But the space complexity is also like a bit worse, but often we don't really like care about like that much about space complexity anymore because we've gotten so much memory, and we just only care about speed. So we can also like set it up or like represent it as an adjacency list, and it will be good to set it up as an adjacency list if we have like dealing with sparse graphs. So this is a sparse graph here where we have these kind of nodes connected in this way, and then the space complexity is only the edges plus the vertices, so we will have less space complexity. But let's say we have a graph here that we want to store in an adjacency list. So it's a linked list where we have this vertex here that like have a linked list here of 20 and 40. So the linked list here will contain the vertices that it can go to. And then we can see that this vertex 20 here can go to either 10, 20, 30 or 40. So this is like how we can set up an adjacency list and represent a graph in this way here. And this is good for a sparse graph, and we can see that if we had a dense graph for example, and we want to represent it as this adjacency list here, like we would have really long linked list, and that will like be kind of a problem. So if we have a dense graph, we often use like adjacency matrices, and if we have sparse graphs, we will use adjacency lists. So here just like another overview of like what adjacency matrix is, and the operations for adjacency matrices when we're using that is also like very time efficient, because like all of the operations with insertion and looking up for elements, it is constant time, so it's really very time efficient when we're doing operations on our adjacency matrix. But again, we give up a bit of more memory to get this time efficiency here. And we also use matrices, which is like good for operations on GPU, because nowadays we normally like want to do something like as fast as possible, and we don't want to use the CPU anymore. Like if we have some operations that we want to like do on a very large like matrix or something like that, or do a lot of different kind of matrix operations, like we just put it on the GPU instead, or like a tensor processing unit or something like that can do the operations way faster than the central processing unit. So that's also one of the pros of using adjacency matrix to represent a graph. So this is how we can set up an adjacency matrix in C++. Where here we just have like a boolean here of the adjacency matrix, which is like where we just have like the rows and the columns, and then we have the number of vertices, and then we initialize the matrix here just to 0. So we just had this two for loops here to just sets the rows and then the columns to 0 here in our adjacency matrix, and then we'll have an adjacency matrix with all zeros. And then when we add a new node, we can go into this adjacency matrix here, and then we can update the index and tell it that there is a connection between these two vertices here. So we add the edges between the vertices, and then we can represent and set up a graph in C++ in that way. So the other one here is the adjacency list, and it's a way to like represent the graph as an array of linked lists, and it's a bit better for memory compared to the adjacency matrix. But we only need to store because we only need to store the values for the edges, as we all talked about. Like we only store like the values here of the edges, and not like the vertices between all of the edges here, which can be good in some different kind of situations. So if we want to implement this adjacency list here in C++, we will just have the number of vertices and then a list of integers here, and then we will have our adjacency list here with pointers. So we can just use this data structure here, list in C++, and then we can have these functions here where we can initialize our graph and add the edges that we want to have in our adjacency list. So we can also have some different kind of algorithms in graphs, which we're going to talk about a lot more in some of the upcoming and future videos. In this video, we're going to focus on the DFS, which is the depth first search and the breadth first search, because we can do this when you have an unweighted graph, or if we want to find like a path, or like we want to find the specific like shortest path in a graph from one vertex to another vertex. Then we can use breadth first search, and if we just want to find a path, we can use depth first search. And then some of the other here, when we have like a weighted graph, we can use some other different kind of algorithms here, like A and Dijkstra, to find the shortest path in a weighted graph. And then when we're talking about minimum spanning trees in another video, we can use the prim and the cross-call algorithms. So this is just to like give you an overview, or like what different kind of algorithms there are in graph. And we're going to talk about more about these like in later videos as well. And we're going to see some different kind of examples on how they work, and also like how to implement it in code and see what they do. So to get the shortest path in a graph here, like we have 4 possibilities to find the shortest path in a graph. So first of all, we can have this unweighted shortest path here, where we have the time complexity is the number of edges plus the vertices, and then we can have like the weighted shortest path and a weighted shortest path with negative edges, and a weighted acyclic graph special case, which is a linear time complexity. So these with the weighted graphs here down here, we're going to talk about that more about when we're more in later videos when we're talking about the A and Dijkstra algorithm. Specifically when we're going to find the short path in a weighted graph. But for unweighted graph here, we can use this breadth first search and depth first search, which we're going to talk about in this video. And we're going to see an example of how we can implement breadth first search in C++. So let's talk about briefly over what like breadth and depth first search is. So breadth first search can be used to find the shortest path in a tree. So down here we can see that we have a tree here that we're going to traverse. Then we're going to traverse it with the breadth first, as the name says. So we're searching our graph here, or like our tree here, with the breadth first search. So we go level by level, and then we search all of the vertices or nodes in our tree or graph when we're doing BFS. So first of all, we have the root node here that we're going to visit, and then we go to the next level and visit all the vertices here. So first of all, we will visit this first here, and then number 2 here. And then when we're done on this level here, we go to the next level and we visit all the vertices here, and then we go to the next level again. Where in depth first search, it can be used to find a path in a graph. So here we go from the root node here, and then we go down in level. So we go in depth first, as the name says. We go in depth first, and in breadth first we go with the breadth first. So we go level by level, but here we go down to the bottom, and then we go like around here and traverse our graph or tree in this kind of like structure here. So we should probably like use breadth first search is over like DFS if it's possible for your application, and if you just want to like find the shortest path, which is like often the case that we want to find. Like often we don't only want to find a path, which like this depth first search here, it will just find a path or like a solution to the problem. But if we're using breadth first search, it will find the shortest, like the actual shortest path for our problem, or like in our graph between 2 nodes. So it will be preferable to use the BFS over DFS if it's possible for your applications, or if you specifically want to use DFS, that's also like okay. But for more practical examples, like BFS is the most used one. So let's jump into the code here and see how we can implement breadth first search and see how it works. So we're now using Sublime Text here, and I'm going to show you an example of how we can implement breadth first search algorithm in C++ to find the shortest path in an unweighted graph. So first of all, here we're going to create the graph class here, where we have this as I showed you in the slides, where we have this adjacency list. So we're going to represent our graph in this example here as an adjacency list. And then we have the number of vertices and the adjacency list that we want to store our vertices in. And then we have a boolean here if that vertices has been visited before. And then we can set up the constructor here for the graph. So we're going to initialize it with the number of vertices that we want in our graph. And then we can add an edge between the vertices in our graph here. So first of all, we have like the source vertex and the destination vertex that we want to connect an edge between. And then we have this function here, breadth of search here, where we have a starting vertex, and then we're going to find the shortest path in a tree, or like we're going to show the different kind of like vertices that we're like actually like visiting when we're doing breadth of search, and we're going level by level in our graph. So let's first of all here create a graph with the given like vertices and maintain an adjacency list. So we're going to represent it as an adjacency list. So first of all here we have this graph constructor here where we just set the vertices to the number of vertices that we initialize it to, and then we create our adjacency list here, which with this new list like data structure in C++, and then with the number of vertices here that we have initialized up here. And then we can add an edge to our graph here. So to add an edge here, we need to have this the source vertex that we're going to add the edge from, and then the destination. So we connect these two vertices here with edges in this function. So first of all, we're going to have this adjacency list here where we're going to take the source vertex here, and then we're going to push back the destination vertex. And then for the destination vertex here, we're going to push back the source here. So we're storing these edges here, or like these vertices here, in our adjacency list, as we showed you in the slides. And then we have this breadth of search algorithm here that we're going to implement, where we have a start vertex, and then we're going to traverse in our graph with the breadth first. So we're going level by level in our graph and visiting the vertices. So first of all, we have this visited here, where we're going to like keep track of if our vertices already has been visited. And first of all, here we're just going to set like all the vertices equal to false, like we haven't visited all any vertices yet. And then we have this queue here, which we're going to implement as a list here to like store the elements on that we're going to traverse when we're going in depth, because we're going to use a queue here because we have this first in first out principle when we're going to use the breadth of search algorithm. And if we were going to implement like the depth first search algorithm, we will use a stack instead, and then it will actually like be some of the kind of the same code. But in this case here, we're going to use the queue because we have this FIFO principle, where in the depth first search we will have the LIFO principle, like last in first out. So first of all, we're going to set the start, like the first vertex that we are going to visit to true, because now we're visited, and then we just push back this vertex here to the queue, so it will be the first element in the queue. And then we have an iterator here for the list, so we can like go through our linked list and check for different kind of like different kind of vertices in our adjacency list. So as long as the queue is not empty, we still need to traverse through our graph. So first of all, we set this current vertex here to the front element of the queue. So in this case here, we just push back this start vertex here to our queue. And then we can just like see out what vertex we have visited now here. So in this case, it will be the front element. And then when we're done visiting this node here, we can pop it from the queue. And then we can go down here and update our adjacency list. So first of all, here we will have an iterator which will go through like the adjacency list for the current vertex that we're in now, and it will go through that until we're at the end of the adjacency list that we're going to go through. And then we set the value here that we're going through with the iterator here to the adjacent vertex. And we can see that we have an if statement here to check like if we have not visited the adjacency vertex, then we will say that we have now visited adjacency vertex, and then we'll push it to our queue, the new vertex that we're going to apply this on, and then the queue will not be empty again. So we will just continue this while loop here until the queue is empty, and we don't have any more adjacent vertices that we're not visited. So this for loop here, you just like run through all of the adjacency list for the vertices, and then we will just check if the vertices has been visited, and if they have not been visited, we just go push back the vertex to the queue, and if they're all visited, we don't do anything because now then the queue is empty, and we'll just go out of scope here, and our function would terminate. So we could use this to keep track of like how many times we have done this, and what level we are at what level we are in our graph, or like in our traversal, and then we can actually like return that, and that will be the shortest path in our graph when we're traversing it. So we can also use this, or like make it as the shortest path in an unweighted graph. So it will just be like that we're keeping track of how many times that we're going like to the next level in our graph, and then we just increment it like we increment one variable for every like level we go down in our graph, and then we can return that value, and that will be the shortest path. So down here in main function, we're actually like going to first create a graph here with the number of vertices here, which is 4. And then we can connect edges here between the vertices in our graph here. So first of all, we give it the starting vertex and then the end vertex. So we can see that we have a vertex here 0 that is connected to 1, and a vertex 0 here that is connected to 2, and a 1 here to 2, and so forth. And then we're going to apply a breadth of search on the second element, or like the second vertex here, because the breadth of search algorithm took the starting vertex here as an argument. And then if we control shift into, or like control B here, it will run the program, and we can see that when we do breadth of search, we first visit the second node here, because this is the first node that we're going to apply. And then after we have here the second node, then we'll go down to the next level. So we will go down and visit the next vertex in the depth, and then go through all of those vertices at that level, and then we will visit vertex 1 here and vertex 3 here. So now we have like traversed around in our graph from this second or like this starting vertex here in our graph. So we start at 2, go to 0, 1, and 3, and we know that we have 4 vertices in our graph. So we have visited all of the vertices here by going at the breadth. So we go breadth first because we're doing, of course, breadth of search. So thank you guys for watching this video, and remember to hit the subscribe button and bell notification under the video, and also like this video if you like the content and you want more in the future. I'm currently also doing an computer vision tutorial in OpenCV with C++, and also an artificial intelligence tutorial where we're currently talking about reinforcement learning and how we can apply Q-learning to have an agent learning by itself. So if you're interested in one of those, I'll link to one of them up here, or else I'm just seeing the next video, guys. Bye for now.